So last time I promised you I'd show you how I created this dissolving object. And it's a technique we rather frequently use, especially when it comes to still frames. That's where this technique really shines. And basically it's not that complicated. What we're going to do is we will advect a VDB using a velocity volume, storing vectors pointing in the direction where we'd like to move our geometry. And the only tricky part here is scaling the length of these vectors, so that one side of our geometry won't be advected at all, while the other side of the geometry will be advected almost so that it dissolves. So let's assume we have some geometry that we'd like to advect, like this here. What we'd like to generate is a velocity field with increasing strength along the length of our geometry. So with a strength of 0 here at this edge and a strength of 1 at this edge. And what we could use to scale our velocity vectors stored in this volume is the position of each of those velocity vectors within the bounding box of our geometry. So when we see this axis as one axis of our bounding box, we can use what's called the relative position within this bounding box to drive the scale of our velocity vectors. Let me show you how. As always, let's drop down a geo node, dive in there, and within the file node, let me just load up a geo I prepared. This is just a poly-reduced version of a geometry of a 3D scan. I downloaded it from 3dscans.com. And the first thing I'd like to do is turn this into a fog volume using the VDB from polygons node here. Fire this in here, and let's decrease the voxel size to say 0.01. Highlight this, and what we want is not a distance VDB, that is an SDF, but we'd like a fog VDB with a filled interior. After that, I'm just going to drop down a volume wrangle here, and make sure that each voxel in my volume has a value of 1. So I'm going to just go here, float density equals to 1.0. So I just set every voxel in this volume to 1. Let's just drop down a volume visualization node here, and visualize this a bit better by increasing our density scale to say 100. We can see now we have this coarsely filled volume here. Next, what I need is a vector field to store the velocity vectors for our advection. And the velocity vectors tell my advection node in which direction and how far each voxel at each position should be moved around. As I'd like my volume to be also advected outside of this bounding box here, we need to create a volume that's a bit bigger than our geometry here. And one SOP that we can use for this is the bound SOP here, which will create a bounding box from our given geometry here, which now is the exact bounding box of our geometry. However, we can dial in some padding here, say 0.6 along each axis. So now my bounding box is as big as my geometry that's coming in here, but it also has got some padding in each direction. Next, let's again use the VDB from polygons to turn this into a VDB. Again, we would like a fog VDB. Dial down the voxel size a bit, and we'd like the interior to be filled. However, this is just a float volume now. So when I middle mouse button on this, it just stores one single float value called density. However, what we're going to need in order to store a velocity is a vector volume. Here comes my quick hack for turning a float VDB into a vector VDB. It's just by dropping down the VDB analysis node with its operator set to gradient, and we'd like to give the output a custom name, vel for velocity. So what this does is, on the one hand, it calculates a gradient, which we won't need, we will override that, but it also created a velocity volume that stores a vector 3 instead of a float. So let's write down some velocity in here by dropping down a volume VOP, and first we are going to write a curl noise into that volume here. So let's dive in here, delete our output, instead drop down a bind export. That's how you export values to a parameter that hasn't got a standard name, like for example vel for our velocity, and it's going to be a vector. And to generate those vectors, we're going to drop down a curl noise node, which on the one hand needs our position input and will output our velocity. And what I'd like to do is promote these parameters here so I can dial in and adjust the curl noise. Let's go up one level, and I can see I have now all these settings here for my curl noise. Let's visualize this by dropping down a grid, maybe scale it down a bit to say 3 by 3, and increase its row and column count. Pipe this into a volume trail SOP here. Points go in the left slot, velocity volume goes in the right slot, and let's highlight it. And we can see now we've got some trailed points here, so our velocity volume is now filled with a curl noise. However, as you can see, the length of my trails is pretty similar across this whole geometry. I'd like these vectors to be very short in here and very long on this side. What we need for this is we need to pipe in this file here, that's my incoming geometry, on the second slot of our volume VOP. and let's hold down Alt while clicking on this connection here to insert those points and lay this out like this so it's clear what's happening here. So on this port here, I've got my basic geometry coming into my volume bob here. So let's dive in there. And in here, I'd like to use this geometry and to check against this geometry where we are in regard to its bounding box. So are we inside the bounding box? Are we outside the bounding box? How far to which end of the bounding box are we? There's a note for this that tells me this, and it's called relative to bounding box here. So let's drop that. And in the file slot, we will wire in the op input 2. That's where my original geometry is coming in. And we would like to compare this geometry's bounding box against our current voxel position here, the P. And this node is going to spit out a vector value between 0, 0, 0 and 1, 1, 1, depending on where in our geometry's bounding box we are currently. And when I look at this viewport and this geometry, the only axis that matters to me is the z-axis here. So let's isolate this by dropping down a vector to float, which will give me this vector's individual x, y, and z component. And currently I only care for the z component, that's the last one here. So let's use that to scale our curl noise vectors here by dropping down a multiply. And I will multiply my velocity vector that my curl noise generated with my z component value, like this. Let's dive up again and highlight our volume trail again. We can see now, on the one hand, the length of these trails hasn't changed much, however their color has. So when we dive in the volume trail here and set the advection method to advect by time, we can see now we get different lengths in our volume trails here. However, what we can see, in comparison to our original geo, when we step outside the bounding box of that geo, our vector length increases again, instead of remaining 0. That is because outside of my geometry's bounding box, the relative bounding box node will return negative values. So instead of remaining at 0, the value keeps decreasing into negative values, and thus my vectors aren't scaled to 0, but are scaled negatively. They are just mirrored, basically. So let's fix that in the volume bob again, and after our vector to float, let's drop down a clamp, and I want to clamp between 0 and 1, and not allow negative values here. And now I can see my volume trails are correctly kept at 0 outside the bounding box here. Okay, one final thing that I'd like to do is I would like to drop down a ramp to be able to tweak how fast those vector trails or how fast those velocity vectors get scaled along my bounding box. So let's go into the volume bob here, and after the clamp, I'll drop down a ramp parameter node, which I'll set to spline ramp, call it ramp bbox position, and wire it in here. Let's go up one level again. Scroll down here, and let's maybe set this ramp here to be a B-spline on both endpoints, and add another point around here. Let's drag that down like so. So you can see now my vector length now increase according to this curve here. Let's save that. So now we built our velocity volume as well, so let's zoom out a bit. Those visualization nodes, let's put them aside here, and let's drop down the star of the show, the VDB advect. And the VDB advect on the one hand takes in a VDB, storing either a surface or a fog volume, that is a density, and it also takes in a velocity volume here. So let's highlight this. And also maybe we'd like to put down the volume visualization after the advection here and highlight this. We can see now it already moved a tiny bit, but not so much. So the way to increase the magnitude of the advection is to increase the time step. And currently when we click on that, we see it's 1 divided by our frames per second. Let's just shift control click on that here, and we have the expression removed. So let's increase our time step to say 0.2. We can see now there's something more happening here. Let's increase it even further to say 0.5. And it takes a while longer now, but it also advected these parts much further away. However, you can see those errors here, and these parts somewhat disconnect. And that is because the advection actually has to trace what is happening to those individual voxels while they are being advected through a volume. And currently, we just only trace one time, which might not be enough for such a big distance. So we'll have to sample our velocity volume in substeps, so to say. So for example, this down here would not directly be sampled like this, but with intermediate steps like this. And the way to do that is, of course, increase the substeps here. So let's dial those up to say 4. And we have to keep in mind that those sometimes might make for a longer calculation. Not in this case. Let's see if we can increase the precision further by increasing the substeps. A tiny bit, but not really much. Let's tweak our curl noise a bit. Let's increase its frequency to say 1.5 along each axis. And also set it to be a simplex noise instead of a Perlin noise. That's more to my liking. And let's still increase the advection a bit by increasing the time step to say 1 here. We can see now we're already hitting the bounds of our bounding volume here, where we store our velocity. So let's increase the size a bit in the bound sub here. This is the upper Z bounding, so let's increase that to say 1. And we now have our volume curling through this bounding box here. Maybe it needs a bit more space along the lower X, so let's set that to 1 as well. Of course it was this one here. Yeah, exactly like this. So yeah, let's unhide this. And this is it. This is our basic technique for dissolving stuff. As I already mentioned, it works especially well for still frames. And the nice thing about it is if you exchange this file here with, say, a null, and instead of wiring in this file node here, for example, let's drop down a font along with a transform. Let's rotate it along its y-axis and scale it down a bit. Let's drop down a hello world here. And let's extrude this. Let's increase the distance a bit and make sure we have a back as well. And let's use that instead of our file and cross our fingers. And we can now procedurally dissolve this piece of text. Of course, we maybe would have to increase our volumes resolution here. We get some block artifacts due to the coarse voxel size, but we could always do that later. So yeah, as I mentioned, rather simple, rather straightforward setup, but also rather versatile in what you can do with it, and also considering the speed with which you can iterate here. So yeah, that's one of our standard tricks from our toolbag. As always, I hope you had fun with this. Looking forward to seeing your artwork, and see you next week.